Thank you, Mehmet. So now this is something we already hinted at yesterday when we were looking at how the images are being dumped. That in principle, every time you make an image, you need to move data to the CPU, and we were only moving the current image, the image that is the data that is being read from. And reading can be done in parallel as many times as you want, practically, almost. And so it would be nice to parallelize this. So while the next heat equation solution is being computed, the stencil is being run, at the same time, I could be using another queue to copy data from the device to the host and then write out an image at the correct moment. So let's do it. It's super easy. All we need to do is create another queue. So let's see, how did we create a queue? Well, we said I want a queue on the ACC, which is non-blocking, and I gave, okay, this queue is for device, my device. Since I want another queue on the same device, I will just copy this. A common way to separate my work is exactly like what we will do. I am separating my computation time. So I'm going to use the time I'm using for computing the next buffer with things I need to do for I/O. So I will call this one my compute queue, and I can call this one an I/O queue or a dump queue. So now I have two queues, and let's see. I will start off with executing the initialize buffer. So, okay, this is something that I need to do on device, nothing related to my host. I will say, okay, please do it in the compute queue. Moving forward, there is something queued in the compute queue. I'm trying to initialize the buffer. We go ahead. And next we get to executing our core stencil. What I want is to make sure that this stencil does not get executed before my initialization is complete. So this goes into the same queue as the initialization. So this things in a queue are first in, first out. So this operation will follow the initialization. Fair enough. What next? I need to apply boundaries. Of course, applying boundaries also needs to be in the compute queue. Finally, I have this mem copy where I am copying things from the ACC, the accelerator device, to the host. And I want to do this in parallel while the compute queue is still running. So, okay, let's see how it goes. I will say that copy stuff using the other queue, and then I will wait for this queue and write the image. Sounds easy enough, yes? Yes, I'm seeing some funny faces in the crowd. Something's not quite right. Well, what has happened here? We have not synchronized our queues correctly. So imagine this. I put work inside my compute queue. I said initialize my boundaries, initialize my buffer, compute the core, apply my boundaries. But these tasks have only been put inside the compute queue, and I have no guarantee if these are actually finished. So when I say that, okay, do the mem copy, and I give it another queue, I'm not waiting for all of this computation to finish before I decide to actually do the mem copy. So we really have a race condition. And most probably this copy will start even before you've started to run inside the core stencil. So this is problematic. And this is why whenever you're doing something like this, you really need to think hard about synchronization. To do this correctly, I will have to wait. I need to wait for my computation to be in the right state. But if I do something like this, did I gain anything? My idea was to parallelize. I wanted to move this current buffer to the host while I was updating the next one. And if I wait after I'm already updating, I gain nothing. So does anyone have any ideas how I can do this? In principle, it should be possible. Yes, Brian.
In theory, we could create something like an event, essentially say we want the dumping to start when the last step has been completed and we are sure that we have a valid state we actually want to know.
So Brian suggests that at the end of a step, maybe we can add an event, and later on, when we are dumping, we wait on this event, make sure it is done, and only dump afterwards. Yes, this is absolutely possible, and we have Alpaca events for exactly such a use case.
But if you if you wait the event at the same position inside the loop, then it's going to be the same thing. With the wait. The wait waits for the compute queue, and event will also wait for the compute queue. It is the same thing. I mean, the position of waiting or event is important.
So this is a very important insight. What was said was that even if we have an event, if we place the event in the same place, we will still wait for the computation to finish. And this really does not solve our problem. And the real issue is the position we're waiting at. So the position where the event would be. And how we can do this is, so you can ignore these macros safely. Sorry about them. So instead of waiting over here, I don't do this. And doing the mem copy over here, what we can actually do is, I only wanted to wait for the initialization to be complete. And before I can start the mem copy before I even start the computation, because I don't need the next step. I don't need the computation to be done. I only need the current step. So I will remove the mem copy from here.
No. Just wait before the loop, then mem copy can stay there.
So the suggestion was to wait
before the loop, wait the compute, wait the compute queue before the loop.
So
just before, not inside the loop.
Before the loop.
Yeah, just about the loop.
So we can write this out. So the suggestion was to wait on the compute queue over here outside the loop to make sure the initialization is complete, and then carry on this way. This way we can be sure that when we are dumping, at least the initialization is complete.
Yeah, initializing is complete.
Okay, but what will happen when say after 100 iterations, I keep on adding to the queue more and more stencil operations. Then when I reach the mem copy for the next one, I have the same problem.
Yeah, you
Because
want the last one.
now I am not waiting anymore on the computation to be complete. I don't know what step I am on when this dump is executed. So this is problematic. Again, this shows why you need to be really, really careful thinking about synchronization. So this does not work. What we really need to do is move it inside the for loop. So what will happen now? Can we reason about this? Initially, this works. This will wait for your initialization to be complete. Your next step is enqueued. You do the mem copy. So you have the correct state for this step. Then you wait for the dump to be complete. There is no way around this. You write the image, then you swap. Going to the next step, you have a wait here. Okay, this isn't the worst thing in the world, because whenever you want to execute it again, this anyways was inside the compute queue. So this wait is basically a very, very tiny operation at best. And you are waiting on things that would have been in a queue anyways. There's someone standing in front of me and I'm waiting for my food, and there's a wait in between us. Well, yeah, there's no way I can jump ahead in line anyways. So will this work? Does this look correct to everyone? Well, maybe 100 iterations later, I'm still in my compute queue. Things look okay. Does this really overlap my computation and communication? It seems so. So let's stick with this. And finally, we can, yes, a question.
Our suggestion, you could extract a variable to say like need write image that would be true only when the PNG writer is enabled and the step -1 modulo 1 is equal to 0. And if this is true, if we need them to update, then we can wait, because otherwise we don't need to wait for the compute queue. And then in the other section, we have just need to wait.
So the suggestion is basically something similar to this, not exactly, but similar. Is this what you wanted? Yes?
With the modulo as well.
And conditional wait.
And only if we do this.
So, I mean, this would probably need measurement to see if there is anything to
But yes, of course, everything you do, especially when you're optimizing at this level, it is extremely important to measure. And but yes, this sounds completely reasonable.
Even more important would be to fix the typo.
Oh no.
The wait to
Thank you. All right, so we have a conditional wait, and we dump for images. We finally have our last mem copy. All of my simulation is complete, well, at least enqueued. I want to copy things back to my host. Of course, this is I/O. I use my dump queue. I wait for my dump queue to be complete, and then I validate my solution. Yes? And we're done. Is this correct? I'm asking you because it is not correct. And really, again, we have to be careful. I'm dumping, but I'm not sure if my computation is actually finished. So I need another wait over here. So I need to wait on my compute queue to be finished. Then I do my mem copy. Then I wait on the mem copy to be complete. And then finally, I validate my solution. And this is the kind of optimization you can get when you're using two queues. Really doing the I/O separately. But the same principles apply to much more common things. For example, if you have MPI communication, you can at many times do the MPI communication in parallel with your next step. Or many other things, asynchronous operations in general can be parallelized this way, using multiple queues. Yes, Brian?
Would it also be possible, instead of waiting for the computer to add the last memory
Yes, so the suggestion is to do something like this, and this is also completely valid because I need to wait for my compute queue to finish and only then do the dump, and there's no benefit of using the dump queue for this. There's no parallelization happening over here, so we can just as well put this operation on the compute queue. Cool. And stray character. Yes.
In a more complex setup, maybe with more queues, you do the same thing with events.
So the question is, if you have a more complex setup, maybe you have more queues, or maybe it is just extremely hard to reason about things like this. Can you do the same thing with events? And the answer is yes. And Alpaca has events which can be enqueued to queues. So I think the interface is really Alpaca event and Alpaca enqueue. And that way you can wait on events on arbitrary queues. And if you find that easier to reason about, or also in some cases, it is the only way you can get the synchronization you're looking for, then please use it. Yes. Of course, we can't cover everything we have in Alpaca in this workshop, but this is a very important area, and I would also totally suggest everyone to look at tasks and queues inside Alpaca events. It's a good thing to know about. Brian.
Is there, from a performance point of view, is there an advantage to using events or not using events? So does it kind of make a difference, or is it just differently overdeveloped?
In terms of the performance, the question is, can using events have a performance impact? Is this correct?
I think it can make it easier if you run on different threads, the driver.
It definitely make it easier to understand what exactly which is your rating on the language. The ask is, does it have a consequence to use this?
In that case, it's not strongly required, but in case you would write your write image as an asynchronous task, so that write image is running in a thread, then so the advantage is you are not blocking your execution. So you could, so if this write image would be an asynchronous task, so maybe a Packer kernel on a host accelerator, then it would be possible that you do not block the execution of your current thread where you can queue all the stuff, so you can go on with your work.
Well, just using that doesn't have.
It's then backend specific.
Okay.
So the discussion in the room basically said that using events, so at least my suggestion would be not to worry about it unless you see this as a real performance impact. But technically, it depends on the backend you're using. So CUDA has native CUDA events. Maybe your backend does not have a very good event synchronization mechanism, so there might be a larger overhead. This depends on your backend, and again, it's important to measure performance, and it is highly recommended. I will try to build this once to see, just check if we have not made any reasoning errors and really our program is free of race conditions. Or at least it's a race condition that we don't see in the first run, and maybe I'm just lucky.
I'm a bit confused now about this condition. Is it not possible if the kernel that computes is much faster than the one that writes the image? Yeah. No.
Yeah. So it seems that we have done things correctly and things are fine. I realized at some point that I added 2 queues in our use chunking example. I hope this does not confuse people.
So if the kernel that computes is much faster than the one that does the copy,
But we use
then it's possible that, because here we start writing, and then we go to the next loop, the next loop performs the computation, then we do nothing, then we go to the next loop, and if we don't wait,
If we don't.
this condition, then it can start computing a second time, but with the loop, and changing the current.
Yes.
Whereas the other one is maybe still copying the memory to the CPU.
So this is an excellent observation. So the comment is, let's assume that the compute is extremely fast. And what's happening is I execute my core, I say for the first iteration everything is fine, I start dumping, and the dumping is in progress. And I keep adding more stencils, and it's possible that at some point I overwrite the thing which is being copied while the copy is still in progress. And thinking about it for a second, it seems like it's true. We really have a problem over here. It is a time for a Kit Kat. Can you pass it along? Yes, so really a lot of people in... Oh, he held it.
I'm waiting for it.
Go for it. So, yes, really we have a race condition over here, and... Or do we? Yes.
No, we should remove the if condition from the first wait. This will make everything correct.
So the comment is, maybe if we remove the if condition over here, this will make things run correctly. Because this makes sure that our previous step is completed.
Yeah.
Don't think it is enough.
Yes, I also don't think it is enough.
I think we need to store like, oh, did we compute something, and are we copying something, and if we have copied in the previous iteration, that we wait until the copy is finished.
No, we are copying the current, the current one, not the next one. The current one is not changed by the kernel.
Yeah, but you could
No, but
run 2 iterations of the loop.
No, because there is wait.
That's only on the compute.
Okay.
Yes. So I think what the discussion in the room has realized is that waiting on the compute queue is not enough. This is not enough for a solution here. You really need to know that the dump is finished before you start doing the next computation, because otherwise you will overwrite the data. It's possible to overwrite the data.
Go down to the dumping.
Yes.
But the write image is a blocking operation.
Yeah.
So you are definitely finished with dumping, and then your control flow is going on.
Yeah, sorry.
So therefore, no race condition.
There is no race condition. So the final observation which fixes all of our problems is that write image is an operation on the host which is not asynchronous, and this operation will be finished, and only then will we move on to swapping and adding more things to the compute queue. So this is not something we have to worry about, thankfully. But again, this is great discussion and insight, because it really shows you, with even such a simple example, it's very easy to make mistakes or oversee little details. Awesome. So with this, I think if there are no more questions, maybe from the online chat, we can move ahead.
Just to raise, there is an ongoing discussion in the Zoom chat regarding exercise or hands-on number 5. It would be great if you can show the code that you implemented before.
Yes. What part of the code?
Specifically the chunking. The chunking hands-on. Yeah.
Yes. So I'm already in the chunking hands-on. I apologize I added the 2 queues in this, but I hope it does not complicate things too much. So this is where we started to deal with chunking. Let me check the chat.
So the timestamp on the chat is 10:55. If you can just look back.
Is it maybe possible to reformulate the current question, because the discussion is longish?
Yeah, maybe I can.
Yes, please.
So the problem, or like the confusion I had, is the chunk size that we define is then used to calculate the threads per block, right? Or like to set the threads per block.
So yes and no. The chunk size is only used to define how you want to split your data. So when you define your chunk size, you don't really care about the threads per block. You should, maybe, but in principle, the chunk size is only a decomposition of your data domain.
But since we are we are saying that each block is responsible with a chunk, therefore chunk size affects number of blocks, because each block is responsible to process a chunk, although block size could be very different than the chunk size. Therefore, chunk size only affects number of blocks, because our data is known, data size is known.
Yes, and just to finish off his statement, so chunk size splits the data domain, okay, therefore it defines how many blocks you have, and the question was about the number of threads in a block. It is only limiting the number of threads in a block if, for example, you have much more threads inside a block than you have elements in your chunk.
Okay, but what I mean is that in line 132, we can basically set the threads per block to the chunk size, in the case that max threads per block is larger than the chunk size prod.
Yes, in case max threads per block is greater than chunk size dot prod, you can directly set the threads per block as chunk size. This is correct.
I'm just a little bit confused what the chunk size means here, because I thought that it would mean the elements per thread that we defined above somewhere. But if I use this example, which works with like how I did it, and then I change the elements per thread above, which is 1 1 by default, and if I change it, for example, to 2 2, I get incorrect results, and I think the work diff is also just wrong.
Yes. So the question over here is, when you use elements per thread, what you are responsible for is making sure that you are handling the correct element for every thread. So we can go into the stencil, for example, and see where you are probably going wrong. So if I say that my thread deals with 2 elements, for example, you have over here an index for your thread, and you check against the chunk size. And so this loop will go over, say, 2 times. Each thread will operate on 2 elements. And inside it,
I think the short answer is the element level is in this kernel not taken into account. Therefore, the mapping from thread indices to data indices is simply wrong, because if you have an element extent by 2 by 2, you leave out 3 elements per thread.
Okay, but I'm confused. Like if I use the normal example that we had with thread elements at 1 1, then I see in the execution that my block thread extent and the grid block extent are both 8 8, which makes sense. And the thread element extent is 1 1, as I would expect. But then the kernel should be called on 64 threads in each block, right?
yes.
But every single call of this kernel should only calculate 1 element, right?
Yes.
Because I have a thread element extent of 1 1. But also in the kernel, I'm iterating over the chunk size, which would be 8 8 again. So aren't we just computing way too much? Like, I feel like the chunk size that I get in the kernel should be the elements per thread and not the chunk size, which is the block thread extent. Or am I just confusing something here?
So, in principle, I understand where you're coming from. You're saying that since we are processing 2 elements per thread in this kernel, even though we've set elements per thread to 1 1, or maybe even more than that, this has to do with how the element layer in Alpaca works at all. And I'm not sure, maybe Rene is a better person to explain how the element layer works.
No, wait. Do you point currently to the element layer at all, or do you say, okay, element layer is now gone?
In my example, I like what I mean where I think it's going wrong. The thread element extent is just 1 1. Or what do you mean?
Okay, that's 1 1. So and if it is 1 1, we start with a thread index within the block, and then move over the full chunk.
Yeah.
This is line 57.
Yeah.
So, and what's the problem there? I haven't understood what the problem is.
I mean, the problem, I think, is that the chunk size that we pass will be 8 8.
Yes, that is correct.
Correct, yes.
Right,
So,
and wouldn't that mean that we, at the end, iterate in these for loops 64 times?
No, everyone starts on his own thread ID, and this is equal then to the data ID, and then we go over, you have it in a for loop, over the chunk size, so the 8 by 8 we only go over. And we have this is not grid thread, it's a thread strided loop. So the increment is the number of threads per dimension for each block. So on the GPU it will be 8, I think. Yeah, it will be 8. So it will be incremented by 8. So a GPU will only visit the loop body once, and on a CPU you increment by 1 until you reach all elements in the chunk size. So then really on a CPU you go for the outer loop 8 times. You visit the body 8 times, and the same for the next line, the 58. You also visit the body then 8 times for the CPU, but on the GPU each loop body is only visited once.
So again, the critical thing to look at here is that we start the iteration from the block thread index, and on the GPU, for example, there can be a thread index which is say 7,7, and that is your initial condition.
And the step is block thread extent. Step is not 1.
And the step is not 1, it is really 8 in both places. So you will start.
I think that makes sense.
Yes. So inside every thread, yes, but this is a very good thing to point out. And
so then final question would be, how would I get the GPU kernel to actually compute multiple elements in one thread?
So
in this example.
So this is actually doing it. So the iteration stops when you hit the chunk size. If my chunk size was not 8,8, for example, let's say it was 128,128. This is much more than the number of threads you can have in a block. So what will happen is you will have say 7,7 over here, and the number of threads you have in a block is say 8,8, for example, or maybe slightly larger, 16,16. But then you would do 7 plus 16. This is still less than 128. And you will keep on iterating inside this for loop until your whole domain, your whole chunk is consumed. So for the GPU, you really are going over multiple elements if needed.
Okay. So the only confusion is kind of that we don't actually use the elements per thread extent thing. Okay.
So here you in the line 132, you could simply say that instead of setting it here to chunk size, you can say set it to chunk size divided by 2. Okay, we don't support the division, so it is something like that. Then you have already what you would like to have, that you process 2 elements or 4 elements per thread, 2 in each direction, therefore 4. So if you hard code here, for example, now vec 2 or something, or vec 4, then you have already changed your GPU device behavior, so that each thread is really computing more than 1 element. So this is only, you only need to change this line on the host side to say, okay, because the number of threads for this kernel, for the stencil kernel, is independent of the chunk size. The only requirement, how it is written, is I think that this must be a multiple of the threads, but maybe it's not required.
No, it's not required.
It's not required. It could still work. So you could simply add any kind of chunk size.
Yes.
Okay, thanks.
Yep. It's cool, and these examples are always available to you to play around. And of course, during the workshop, we don't have time to go over everything. So even if you realize later on that, oh, I was playing around with this example and I'm still not sure, you can contact us after the workshop as well. There is a lot you can play around with. I would suggest trying different chunk sizes, different node sizes, and we can discuss this also, even if you come up with questions later.
So since this workshop material is completely on GitHub, feel free to open an issue in this repository where we have the data also, because then you can also link directly maybe to a code example to the line where you have maybe a question to, and we could also answer it in an issue. So don't be shy to open an issue. Issues are the right way to communicate with us, because this communication will scale. Other users can help you, developer can help you, maintainer can help you. So at any point.
And the whole discussion will be public, so other people can also be helped by your discussions.
They can also point to code changes in their own fork of the repository.
Yes, you can also point to code changes in your own forks. So please feel free to communicate to us via issues. It's ideal. So this is nice. Thank you for speaking up. I enjoy talking to people a lot more than reading chat. So everyone, please feel free to unmute yourself if you have questions. So what we did right now was adding 2 queues to our example. And we will have one final optimization, which is to add shared memory to our example. And this is a GPU specific optimization, and Mehmet will explain a little more about it.